This video goes along with Lesson 16 in your text, where you'll be introducing the idea of the mole to your students. Now up to this point we've been making lots of compounds and using subscripts to indicate the number of atoms of each ion we need to make a stable compound. For example, in the case of sodium chloride, we use subscripts of 1s here to tell us we needed 1 sodium atom for each chloride atom to make the stable compound of sodium chloride. Now the idea of the mole brings in the relationship between atoms and then grams of a compound, which makes it a much more practical use of this whole idea of making compounds. We can take where we're counting atoms versus weighing out grams of a compound. Okay. Now the big idea here is the atomic theory says that atoms are extremely small. We can't count individual atoms, so we need some relationship to show an amount that we can actually weigh out, visualize, and therefore create a compound. Now this idea of the mole was developed by a chemist by the name of Amadeus Avogadro, and his idea says that in one mole of any element, okay, there are 6.02 times 10 to the 23rd atoms. Okay, so in a mole of any element, so any element that we look at here on our periodic table, 1 mole of any of those elements has 6.02 times 10 to the 23rd atoms. Now this number here is known as Avogadros number, and the important thing here to point out to your students is that no matter which element you look at here, if you were to get 1 mole of it, you're going to have the same number of atoms. Now, a way to help your students visualize that is we're going to use some styrofoam cups here, and each of your students will need 2 cups, and then have them write on those cups 1 mole, and I have them write it several times, 1 mole on each cup, okay, and then also have them write Avogadros number, okay, so that they'll know that when this cup is full of whatever we put in it, we're going to have the 6.02 times 10 to the 23rd atoms of that ingredient. And also for them to get a better idea of what this scientific notation number here, the 6.02 times 10 to the 23rd, is to have them write it out in long form. So the 10 to the 23rd means we're going to move the decimal place 23 places over to the right. And so if we were to write that, and I encourage you to write this on the board for your students, it would be 6.602, and then we'd have 21 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, and so then we can set our decimal place and then put some commas in here. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then right there. So that's our total number of atoms that we'll have in 1 mole of any element on our chart there. And then so with your students with their cups is have them go ahead and write that out. Here I've got it 602 and then 21 zeros after that. So next, what you'll need to have for your students is 2 different substances, and we're going to, for this activity, we'll call them our elements. And you'll want something that's rather dense that you can put in one, and I'm going to use popcorn. You can use beans, you can use sand, I've used gravel before, anything that's a dense, heavy substance. And then as a contrasting substance, you'll need something that's very low density, and here I'm going to use cotton balls. So what you'll want to do first is have your students fill their cup, their containers, with each of these substances. And let's see how we can do this. Try not to make a big mess. Okay. So we'll fill this with the popcorn. Okay, so we can tell your students once they have it filled that this represents 1 mole of the element popcorn. In this container, there's 1 mole. It represents 6.02 times 10 to the 23rd atoms. Okay, so that's 1 mole of popcorn. Then we'll do the same with our cotton balls here. And we'll just put those in there. Get a few more. And we'll just put those right in there. This little guy. Okay, and again, we have your students hold them up. This is 1 mole of cotton balls. In it are 6.02 times 10 to the 23rd atoms of cotton balls. Now, at this point, you can show your students, if you go back to that sodium chloride example we started with here, where we put a 1 and a 1, this was our +1 and a -1 charge, so our subscripts were 1 and a 1, that instead of saying 1 atom of sodium and 1 atom of the chloride ion, we can say 1 mole of the sodium atoms and then 1 mole of the chloride atoms. And you can liken it to your popcorn and your cotton balls here, saying that here's 1 mole of sodium and 1 mole of the chloride atoms. Okay, now the next big point to make with this demonstration is the mass of each of these different elements. Okay, now obviously we've chosen a very dense substance for one and a very low density one for the other to show your students that while we have the same number of atoms of each element present, they don't have the same mass. They don't weigh the same. A mole of popcorn has a much greater mass than a mole of cotton balls does here. Okay? The big point to make though, even though there's the same number of atoms in each, they don't have the same mass. And you can go back to your discussion of the relative mass of the subatomic particles. I believe it's in lesson 3 in your text, where we talked about the mass of an electron is very lightweight, low mass, like a ping pong ball, or I have a styrofoam ball here, compared to the mass of the protons and the neutrons, which would be like a bowling ball if you compare the two, or a cannonball, compare the two. Okay, so we've got this popcorn here and our cotton balls here. Obviously, this has a greater mass, which means that the individual atoms here must have more protons and neutrons in the popcorn per atom than there are per atom of the cotton balls. And at this point, you can take your students to the periodic table and just start with carbon and tell them that the atomic mass number, okay, not the atomic number, which was 6 in the case of carbon, but the atomic mass number, which is usually the decimal number, tells you the number of grams it takes to make 1 mole of that element. So in the case of carbon here, which has atomic mass number of 12.0115, and we can round those to whole numbers if you like, the atomic mass of carbon is 12. So in order to have 1 mole of carbon, you would need 12 grams of carbon. Okay, so if we had a cup that contained 1 mole of carbon, it would weigh 12 grams. Another example, if you go next door to nitrogen, atomic mass for nitrogen is 14 grams. Okay, so 1 mole of nitrogen weighs 14 grams. And you can compare, how does an atom of carbon compare to an atom of nitrogen? Well, if you look at the atomic numbers, you'll know that an atom of nitrogen will have 1 more proton and 1 more neutron than an atom of carbon will, and therefore it must make sense that it would weigh more. Okay, so again, the point we're making here is that we have a mole of each, okay, which has the same number of atoms present in each, and we can then use that when we make our compound here, okay, because we can actually physically get a mole of each part of that compound, okay, and then because the atoms have different varying numbers of neutrons and protons in them primarily, they don't weigh the same. Okay, now to bring this a little more into a realistic perspective, I was able to find some BBs here. Now these are just copper coated BBs, but we can pretend that they are solid copper. Okay, and if we were to get a mole of copper, okay, you can ask your students, how many grams of copper would it take if I needed a mole of copper to make a compound? So obviously your students should find copper on their periodic table. It's number 29, and the atomic mass there of copper is 63.5. Okay, so they would need to get a mole of copper, they would need 63.5 grams of copper. Once they had 1 mole of copper, they could say, well, that's equivalent to 6.02 times 10 to the 23rd atoms of copper. Another easy to get element is aluminum. If you have some aluminum foil, you can ask your students, well, how many grams of aluminum would it take to make 1 mole of aluminum? The same way they find aluminum on their chart. Its atomic number is 13. Atomic mass is about 27 grams. And so it would take about 27 grams of aluminum to make 1 mole of aluminum, which again is, and then if you have a mole of aluminum, you know you have approximately this many, the Avogadros number of atoms of aluminum, and then therefore you can put it into a compound. Let's look at that for just a minute. Let me get the BBs out of the way. Okay, let's say we have compound. Let's just do aluminum chloride here. Aluminum chloride, recall aluminum, Al charge is a +3, chlorine -1, so it takes 1 aluminum atom for every 3 chloride anions. Okay, so if we were to want to prepare or get enough of each set of atoms to create some aluminum chloride, instead of saying 1 atom of each, we can now say 1 mole of aluminum. So we need about 27 grams of aluminum. And then if our chlorine, if we go ahead and look at find chlorine on our chart, it's number 17 here, and the atomic mass is about 35 grams. Okay, and so we need 3 moles of chlorine. Each one weighs 35, so we take 35 times 3, 15, 105. Okay, so we would need approximately 105 grams of the chlorine atoms, and then 27 grams of aluminum, and together we would have the right combination of atoms then to create stable compound aluminum chloride. And these are definitely 2 amounts that we can physically weigh out in the lab. We don't have to count atoms to get enough atoms. We can just say, if I have 27 grams of aluminum, I know I've got 1 mole, which is 1 mole of aluminum. If I have 105 grams of chlorine, I know I have 3 moles of chlorine. If I put those together, I should be able to make the stable compound aluminum chloride. And that's pretty much what this whole demo is about, is making the point that while you have 1 mole of each element, you've got the same number of atoms of each. They don't weigh the same because the relative masses of the particles vary as you go from element to element across the table. However, you have the same number of atoms of each. You don't have the same mass of each, and that's the atomic mass number that you find on the periodic table.